All right, so welcome back, everybody. Apparently, I guess my laptop, my iPad must have updated, so I don't know how to get rid of this monitor in the corner of the screen. So, well, I guess we'll have to live with it. And thank you all for your projects, which I have started to read, and I hope to have all of them done and get you feedback before the end of the week. Right, so we have a little bit of, are there any questions before I get going? Thanks to Joaquin, who's taken over grading for me for the second and third assignment. So I think you should have your second assignments back now. Okay, so we have a little, so the next thing is to prove stability, at least in the compact case of our definition of CDKN. So we know that the set of CDKN spaces is pre-compact. So it has a limit as a metric space. Any sequence of them has a limit, has a subsequence converting to a limiting metric space, but we'd like to see that the limiting metric space is also a CDKN space. So we're going to need to know, and remember the way that we test CDKN is by looking at convexity properties of the entropy along geodesics. And so it's going to be very useful for us to know that when you have a sequence of metric spaces converging to a limiting space, that geodesics in the sequence of spaces converge to a geodesic in the limiting space. So let me start out by proving that. And right. Oh yes. So in fact, let me first introduce a bit of notation. So I'm going to say by geo of x, what I really mean is geo of xd. And what I have in mind is the set of maps from the unit interval into x such that d sigma s sigma t is t minus s of d sigma 0 sigma 1. Right, so it's the set of d geodesics in any metric space. And another little definition, so this is a definition. Another definition, when I have an, I don't know, epsilon isometry or R isometry, F between two spaces, then it has, it always has an approximate inverse. F prime, which goes the other way, or maybe I should call it F tilde, I'm not sure. Maybe I'll call it F tilde. F tilde taking y to x, or F star would probably be a good notation too. Yeah, I like that. Maybe I like the F tilde. Such that, which can be defined as follows. So what do we know? We know for every y in the target, because the image of x under F is an R net in the target, for every y in x, there exists, in y rather, there exists a point in the base, in the initial space such that the distance in the target of y to f of x is less than r. And so I'm going to set f tilde of y to be x. And then it's not too hard to check that, so I have a couple of claims. F tilde is a 3R isometry. And when I compose F with F tilde, the distance of F tilde of f of x is not too far from x. So that'd be the distance in X, I guess. And similarly, the distance in Y of, sorry, one of these is 2R and the other one's R, and I'm not sure which is which. The distance in Y of Y to F of F tilde of Y is, again, one of them is 2R and the other one's R. So if you want to be safe, you could put 2 in front of them. I think that I maybe have it right now, but so let me see. So if I have my set of X's over here and my set of Y's over there, and I have 2 Y's, Y and Y prime, I guess. So if Y comes, so if I have an X and an F of X that's close, so this distance is no bigger than R. And similarly, I have some X prime over here and F of X prime. This distance is no bigger than R. Then what I know is that the distance F of X prime, F of X minus distance X, X prime is less than R. That's what it means to be an R isometry. And the distance F prime of X from Y prime is less than R, and the distance F of X from Y is less than R. And so finally, I get that the distance X, X prime is d F prime F plus R, but that's less than d Fx prime Y prime plus dy prime Y plus d YFX plus R. And so that's all less than 3R plus dy prime Y. And this is the F tilde Y, F tilde Y prime. So we just check that F tilde is a 3R isometry. And it's equally easy to check these other 2 facts here, that when you compose F with F tilde in either order, you get something that's not distorting things by more than 2R. Okay. And so then there's this kind of generalization of the Ascoli-Arzela theorem that I'm quoting it from, I'm quoting this from the paper of Lott and Villani, which finally appeared in the Annals. I don't remember when, about 2009. But in fact, they refer to the proof to Gromov's book or to an earlier, the appendix of Appendix A of Grove Peterson 1991 JDG article. And it's basically Ascoli-Arzeli, but a non-smooth version of Ascoli-Arzela. And it says that if I have a sequence Fi taking Xi onto X, and Gi taking Yi onto Y, are epsilon I isometries between compact metric spaces with epsilon I going to 0. as I goes to infinity, then let f tilde I, which takes x to xi, and g tilde I are the approximate inverses defined above. And finally, I have some other map. I guess I'm going to call it HI from, maybe I'll put the i's, maybe I'll keep the i's in superscript. A set of maps from each of the approximating spaces in the X sequence to the Y sequence are, they call this asymptotically equicontinuous. And what all that means is that equicontinuity would mean for every positive delta, there exists epsilon, rather, there exists a delta. And here there exists a delta and an n, such that whenever I is bigger than n, the distance in xi of, let's say, xi to xi prime less than delta implies the distance in the yi's of hi of xi to hi of xi prime will be less than epsilon. So in particular, these HIs don't need to be continuous maps. Any given HI is not necessarily a continuous map, but somehow what's happening is that as I tends to infinity, it's tending to become more and more continuous. Right? So for any given epsilon, there's a delta and an n, but if you want to take epsilon smaller, then you not only need to tell delta smaller, you'd also need to take I larger in order to get this closer to being continuous. And so what's the conclusion of this? This is the hypothesis of this kind of Ascoli-Arzela theorem. And the conclusion is then a subsequence of the maps. So I want all my maps to be defined on the same space. And it's going to be, so it's going to be maps from X to Y. And so first I'm going to apply Fi tilde to get back to Xi, and then I'm going to compose with Hi, and then I'm going to compose with Gi. And in that way, for every I get a map from X to Y. And then the claim is that a subsequence converges uniformly to a continuous limit. Right, because the epsilon i's are going to 0, the Fi tilde and the Gi don't distort continuity too much, and the Hi's are sort of continuous at scale epsilon for I large enough, and so they're continuous at arbitrarily small scales, and in fact equicontinuous at arbitrarily small scales as I goes to infinity. And so the point is that the maps are possibly discontinuous, but the limit is continuous and the convergence is uniform. And so the proof of this is basically just like Ascoli-Arzela. You use a diagonal process to make it converge on a dense subset. And boy, I wonder if we don't want the the X to be separable. So maybe let's make this Polish. If I'm going to do an Ascoli-Arzela proof, then I need that to be Polish. then I make converge on a dense subset, and then I show that I have enough continuity and equicontinuity around an approximate continuity that it converges everywhere, and that the limit is continuous. And in fact, I'm not worried about making X Polish because I actually really only want to apply this. So you're welcome to try to prove this yourself. But I really only want to apply this in the case with X is the unit interval and Fi is the identity map. And so it can be its own approximate inverse. And so because the corollary that I want to get out of this is, oh yes, right. I wasn't super careful in my statement here, but I want the spaces to be compact as well. I probably want both spaces to be compact. So of compact spaces. And then I don't need it to be Polish anymore because I have compactness. So compactness implies that the existence of a countable dense set. Okay. And I'm going to, as I say, I'm going to apply it to the unit interval where the Fi and its inverse are the identity maps. And really all I want to get out of this generalization of Ascoli-Arzela is that the HIs are going to be geodesics. And so HI is going to be a map from the unit interval into, I guess, YI. And I want to get that when I have a sequence of geodesics in a sequence of spaces that are Gromov-Hausdorff converging to a limiting space Y, then the sequence of geodesics converges to a limiting geodesic. So the corollary that I want to get, which is I think 4.3 of Lott and Villani's paper, is that if the GIs, sorry, yes, the GIs. If the GIs are epsilon I isometries of compact spaces with epsilon I going to 0, and if I take a sequence of geodesics, so sigma I, a geodesic in YI, then GI composed with sigma I converges uniformly to a limit sigma, and sigma's in a geodesic in the limiting space. And it's a subsequence, of course. Are there questions? And obviously, yeah, okay, that's really what I want. And obviously the length, which is in the distance in YI of sigma I0, sigma I1, converges to the distance in Y of sigma 0, sigma 1, because these mapping GIs are epsilon isometries. So the difference between these two quantities is controlled by epsilon, which is going to 0. So the length of the limiting geodesic is the limit of the lengths of the approximating geodesics along the subsequence. Okay. So we basically apply the lemma. So the lemma shows the supremum of t in 0, 1 of the distance in the limiting space between gi sigma I t and sigma t right, I guess I could say along a subsequence. And it provides this limiting object, but so far all we know is about the limiting object is it's a continuous map from 0, 1 into y. And what we want to check is that this limiting object is actually a geodesic, right? So of course the limiting distance, so for every s and t in 0, 1, the limiting distance between sigma s and sigma t then can be estimated. So by the triangle inequality, it's so I'm always going to take I won't relabel the subsequence. But I'll have distance gi sigma is, gi sigma it, and then finally I'll have distance gi sigma it to sigma t. Now all these distances are in the limiting space. But we know as I gets large, right, by this uniform convergence, we know that as I gets large, the first and the last term go to 0. So this is something that goes to 0 as I goes to infinity. And the middle term also, because the GI are epsilon isometries up to, so this would be less than epsilon I, which also goes to 0 as I goes to infinity, plus the distance in yi of sigma is, sigma it. And now the sigma i's were geodesics in yi's. So that's something that's little o of 1. Let's keep the epsilon I, plus s minus t, the distance in yi of sigma I0, sigma I1. And well, I have these wait, this is a slight bit of a mess. Oh yeah, right. But this again is approximate. This is less than the distance in y infinity again of gi sigma I0, gi sigma I1, where the gi maybe adds another epsilon times s minus t, but s minus t is less than 2. So so let's say it's less than 3 epsilon. And so finally therefore taking I to infinity, what I finally get is that the distance y in sigma s sigma t is less than s minus t. I guess I need one more triangle inequality argument to say that as I goes to infinity, these things converge uniformly to dy sigma 0, sigma 1. Right, this term here would be less than d gi sigma I 0, sigma 0 plus d sigma 0, sigma 1 plus d sigma 1 gi sigma I 1. And the first and third terms are going to 0 uniformly as I goes to infinity. And so I'm left with this. Great. And so, and this was exactly the inequality. As soon as you have that inequality, you know that equality holds because of the triangle inequality, right? So, we did this once before, but d sigma 0, sigma 1 is always less than d sigma 0, sigma s plus d sigma s, sigma t plus d sigma t, sigma 1. And so if this is less than s minus 0 times, and this is less than t minus s, and this is less than 1 minus t, all times d sigma 0, sigma 1, which is what we just checked above, then adding these things up, we get equality. And so the inequalities have to be equalities throughout. Okay. So if we have a sequence of epsilon isometries and we have a geodesics in the approximating spaces, the limit of those geodesics will have a subsequence. For a subsequence, those geodesics will converge to, composed with the epsilon isometry will converge to a geodesic in the limiting space. And of course, the geodesics that we're interested in are going to be geodesics of probability measures. And so another crucial proposition for us. Now, this is inspired by 4.1 of Lott and Villani, but they botched the statement, so I had to correct it. So if I have an R isometry or an epsilon isometry, of compact spaces, though I don't think it matters much, then of course F push forward is going to be a map of probability measures on X into probability measures on Y. And even though these are compact spaces, so all measures have second moments, I'm going to put a sub 2 on these things just to remind myself the metric. The distance function I'm using on probability measures is the 2-Wasserstein metric, the Cantor-Rubinstein-Wasserstein metric with exponent 2. I guess any exponent bigger than 1 would work for what would probably work for what I'm about to say, but we'll use 2. Then this is 7R. So if this was an R isometry, this is a 7R isometry. And again, of compact spaces, because we know that when X is a compact Polish space, then P2 of X is a compact Polish space. But the point is that if I have an approximate isometry between the underlying spaces, it leads to an approximate isometry between the set of measures on those spaces when metrized by the 2-Wasserstein distance. Are there questions about this statement? Right, okay. So So they didn't have 7R here. They said they had some horrible formula, and I'm pretty sure I found a mistake in their proof. Okay, so given any pair of measures, on the initial space X, I'm going to let gamma be the joint measure having those marginals, which is d squared optimal. And then I'm going to set gamma prime to be the image of gamma under F cross F, where F is this R isometry. And of course, that will be a joint measure on Y cross Y, and its marginals are going to be F push forward mu naught and F push forward mu 1. And moreover, now I need to estimate the 2 Wasserstein distance in Y of these image of the image of mu naught mu 1 under F push forward. And I'm, of course, it's going to be less than whatever because this has the right marginal, it'll be less than the integral in Y cross Y of dy y prime squared against d gamma prime. And since gamma prime is a push forward measure, that's the integral in x cross x of dy of fx prime squared d gamma xx prime. And so now I use the fact that F is an R identity. So this is less than dx of xx prime plus R squared d gamma xx prime. And so that's less than, on the one hand, R squared, and on the other hand, since gamma is the optimizer, d2 in x of mu naught and mu 1 squared, and then there's the cross terms that come from squaring this, and the cross terms are 2r integral x cross x of dx x prime d gamma xx prime. And then by Jensen's inequality, that is going to be less. So Jensen says that integral f d gamma squared is less than integral f squared d gamma, because gamma is a probability measure. And so taking the square root on both sides, I get r squared d2x mu naught mu 1 squared plus 2r d2x mu naught mu 1. And then I can collapse. So this is, again, this is r plus d2x mu naught mu 1 squared. And now finally I can take square, sorry, this should have been a square. I can take square roots and get that dy2 of the push forwards through f of these two measures is less than d2x of the original measures plus r. So that's half of what it means. Right, okay, hang on. So that's not, this looks pretty good. Oh, I'm slightly confused. So what was I trying to show? I'm trying to show that the mapping F sharp from measures on X to measures on Y is 7R isometry. And it seems too good to be true. But it seems like I just showed it's an isometry. Of course, I need a little bit more to show it's an isometry. I also need to show that I also need F push forward P2 of X to be an whatever a 7R net in P2Y. But again, I think I get something better than that. So maybe I get 2R. Oh, wait. No. That seems to be, so somehow this is, what I'm getting was better than what I had in my notes, but anyhow. Okay, and so finally, so there we're going to use this, we're going to use this last part of, I have to go all the way up. We're going to use these facts that F tilde composed, the approximate inverse composed with F is close to, does distortion not more than 2R. So my claim is that for every nu in the probability measures on Y, I can look at F push forward, F approximate inverse push forward of nu, and since the distance in Y of F composed with F tilde of Y is less than, I can't remember, was R or 2R. I think it was actually R, but maybe it was 2R. We weren't careful to check it today. Basically, I have a Monge map here, which takes this measure to that measure. And so it's telling me that the 2 Wasserstein distance in the probability measures on Y between this measure and this measure, which is to say this measure, is going to be less than, I guess, 2R. Right? It'll be the square root of the integral of something that's no bigger than 2R squared against nu, so it's going to be 2R. And should that so this, and of course this guy here is in the image under F of the probability measures on X. And so this guy here, given any new, I can find a guy here that's in this set that's distance no bigger than 2r from it. So maybe, so somehow, if this 2 can be reduced, so I think that I can actually reduce the 7r to 2r and maybe to r in this proposition. But the point is, I don't really care what the isometry is, as long as when this r goes to 0, this thing goes to 0 as well, because that shows that if I have a sequence of xi's which are Gromov-Hausdorff converging to a limiting space y, then the probability measures on that sequence, compact spaces, will converge to the probability measures on the limiting compact space. So the corollary is if dgh of xi x goes to 0 along a sequence of compact spaces with compact limit, then dgh of p2xi p2x goes to 0 as well. Questions? Okay, so now I think things are going fairly well. So we now know that when we take, if we have geodesics in the approximating spaces xi, d2 geodesics in xi, then we can extract from our Ascoli-Arzela type result a geodesic in the limiting space p2 of x. And it will have, its length will be the limit of the lengths of the approximating geodesics along a subsequence. So the other thing we need to know is, how will the entropy behave along such limits? And so again, the proper proof is in Lott and Villani, but the citation that I wrote down a version of the theorem. So by the way, if you try to read this stuff in Villani's long book, it's terribly convoluted and terribly complicated. So that's why I somehow went back to the paper by Lott and Villani. But in Villani's long book, you have a proposition 29, but I'm going to state a much simpler version of it, which will be sufficient for our purposes. So I'm going to let XD be a compact metric space. And I'm going to take 2 non-negative Radon measures. So a reference measure mu and m and a measure mu, but I'm going to take them both to have finite mass. And one of the reasons it's terribly convoluted for several reasons. One of them is that he has this characterization of geodesics that he likes in terms of, if you have a Polish space, so maybe, yeah, let me have an aside from the proposition, but I'm going to come back to stating the proposition, but I'll just have this aside. If XD is Polish, so is the set of continuous maps from 0, 1 into X under the Spremum norm. And Villani likes, and of course the geodesics on X are a subset of C01. And so Villani likes to represent, he has this notion that he calls dynamical transference plans. And so instead of talking about Villani, and this started a lot in Villani's paper, actually, Villani likes to represent a D2 geodesic UT, T between 0 and 1, in the space of probability measures on X, using a joint measure, which you call, I guess I'll call it capital pi, which is a probability measure on geodesics. So it's a measure on curves. And such that mu t is the push forward through ET of capital pi, where ET takes a curve gamma in geodesics and returns, sorry, a gamma is probably lousy notation since I tend to use that for measures. It takes a curve sigma in geodesics and returns its value sigma t in X. So ET is the mapping from curves in the metric space to the metric space. And of course, it's pretty clear. If you think of these, we thought of these geodesics as arising from joint measures gamma on the set of joint measures having mu naught, mu one as marginals. Now, if you have a measurable selection, you can, so I construct pi using a measurable selection. Let's say, maybe I should call it sigma. Sigma that takes pairs of points x, y, and x squared to geodesics sigma x, y in geo such that sigma x, y 0 equals x and sigma x, y 1 equals y. So if you can, so in order to do a measurable selection using the Narduzzi whatever theorem that we talked about earlier, you need to know that for every pair of endpoints x and y, the set of geodesics joining them is closed, and limits of geodesics are again geodesics, but both of those things are easy to check. Now this is kind of a non-constructive proof because the existence of measurable selections goes through the axiom of choice, and Villani and Lott give a constructive proof. But so somehow one reason that things are complicated from my point of view is they, instead of thinking of geodesics in the underlying space of measures, they like to think of these measures on the space of paths that give rise to geodesics through this push forward formula. Another reason that is complicated is that he didn't use this notion of entropic convexity, entropic CD, which depends only on Boltzmann's entropy, the rho log rho entropy. So before Urvada, Urbar, Kawada, and Sturm came up with this notion of entropic curvature dimension, people used Boltzmann's entropy only to talk about CDK infinity, and they used entropies of the form integral rho to the n, or maybe to 1 minus 1 over dimension with respect to the reference measure, with rho being d mu dm. They would ask, so this would be called, I don't know, the Rényi entropy. Some people call it the Rényi entropy. For CDN0, basically is equivalent to asking for convexity of this along D2 geodesics. And CDKN is actually hard to write down in terms of either this thing or the Boltzmann entropy, unless you have this notion of KN convexity. And so there were these very complicated formulas, and he has to deal with these very complicated formulas because he has this very complicated definition. But of course, the payback that he gets for adopting this complicated definition is he gets the sharp constants in things like the Bishop-Gromov inequality, where we got constants that weren't quite sharp. And it's a big rigmarole to show that his definition is equivalent to ours, which is essentially achieved by Cavaletti and Millman in a paper that may someday appear. It's been a preprint for almost 10 years, or at least 5 years. Okay. Fair enough. So let's come back to this proposition. So if I have two radon, so I don't have to deal with all kinds of, I don't have to deal with all these other possible energies. I only need to deal with the rho log rho energy, and that simplifies statements like the following proposition. So setting mu of rho to be rho log rho, so it's Legendre transform, you can calculate to be the exponential of, sorry, I should use a different letter for the transform variable. So the Legendre transform is a function of s, let's say, you can calculate to be e to the s minus 1. In other words, the derivative of u composed with the derivative of u star equals the identity map in both directions. That's how you check that you've correctly found the Legendre transform. Yields the following formula. It yields that the relative entropy of mu with respect to m, which, of course, this was integral d mu dm log d mu dm dm, as long as, let's say if mu was absolutely continuous with, well, let's say if mu was in the set of measures on xdm with finite entropy. This was the definition, and this also turns out to be the supremum over continuous functions of integral phi d mu minus integral u star of phi of x dmx. And I could also take the supremum over L infinity functions, bounded functions, bounded measurable functions. Right. So there's this proposition, and I'm going to be schematic, a little bit schematic. Lott and Villani again give a long, so somehow this was a theorem in the paper, but it became a proposition in the book. And in the paper, the proof takes several pages, but the idea behind it is really simple. And so let me just give the idea of proof. Well, what does it mean to be a Legendre transform? One thing it means is that u of d mu dm is the supremum over values of phi, phi times d mu dm, and minus the Legendre transform. Because, okay, so u rho equals rho log rho. If you remember what that looks like, it looks like this. It's plus infinity over here. This guy is a, maybe I should define it to be 0 at 0. It's lower semi-continuous and convex. And so that means that it is itself the Legendre-Fenkel transform of its Legendre transform. And so I have this formula pointwise. And now the idea is integrate it. So with respect to m. So therefore the integral of u d mu dm dm is the integral dmx of the supremum. And if you think, I don't know, think about x, think about replacing the integral by a sum. And So the basic idea is I would like to pull the supremum through the sum, but the other idea is that I can choose the phi however I like at the different points in the sum and x, and so so somehow if I could commute isn't that what the theorem is? Commuting the sum and the interval. Sorry, where's my statement of my theorem? Here it is. Yeah. So basically, I had this supremum inside the integral. I would like to pull the supremum outside the integral. And so the only question is, can I commute either in the space of continuous bounded functions or in the space of L infinity, and have integral dm. Sorry, there should have been a phi here. Phi of x. So integral phi phi of x d mu dx dm dmx minus u star composed with phi dm. And then basically these m's cancel out if you like. And so that's supremum over a phi. Where the first measure is, the first integrals with respect to mu and the second integrals with respect to m. So apart from this question of interchanging the supremum with the integral, that's the proof. And what is this thing good for? It's very convenient for several reasons, but so here are the corollaries that I want to harvest from this representation of the relative entropy of mu with respect to m. And again, coming back to the number of Villani's book, this is parts 1 and 2 of theorem 29.20. So it's lower semi-continuity and contractivity of entropy. And so the statement is that for XD compact, as before, and mu and m Radon measures, S mu m is jointly lower semi-continuous in both variables. In mu, sorry, I should try to make it so you can distinguish my mu's from my m's. And moreover, if I look at the image of both mu and m under the same map F, then the entropy goes down. And so that's a little bit, it's a little bit like thermodynamics. Although probably the signs are backwards, but I mean, somehow, you know, there should be less information after I push these measures forward through some mapping F than there was before. And so there's some kind of monotonicity under loss of information for any measurable map F taking X to Y onto another compact space. So these are the two things I want to get. I want to get that when I take weak limits of a sequence mu k mk, the entropy can never jump up, it can only jump down in the limit. And when I take images of mu and m under some measurable mapping f, the entropy can only go down, it can't go up. And both of these things follow from this representation formula here. So let's do the proof of the lower semi-continuity first. So proof what did we have? We had phi d mu minus u star composed with phi dm. So as long as phi is continuous, then this term here is lower semi-continuous with respect to mu. M doesn't appear. And since u star is also continuous, right? U star was exponential s minus 1. Bound, and phi is going to be bounded. Well, the spaces come back, so continuous functions are bounded. So this is going to be a continuous bounded function on the range of phi. So this is weak star continuous with respect to m, and mu doesn't appear. And basically, it's a supremum of weakly continuous functions of mu and m. And whenever you take a supremum of continuous functions, you get a lower semi-continuous function. Weakly LSC in mu and m. So that's very easy. And the picture to have in mind is if you think about a function like this, then I can approximate that by a sequence of functions that do like this. So on some scale minus epsilon around 0. So the red guys are continuous. As epsilon goes to 0, they converge to the black guy. The black guy is discontinuous, but it's still lower semi-continuous. And the black guy is the supremum of the red guys. So it's weakly lower semi-continuous, even though it was continuously approximated from below. And the other property is almost as easy to prove. So what they call the contractivity of the entropy. So now I want, so that was the proof of 1. This is the proof of 2. So as long as the spaces are compact, there's no, maybe I should have, this is another aside. Well, I'll make it in a moment. There's no problem with defining the entropy because Jensen's inequality tells you the entropy cannot, the negative part cannot go to minus, the integral of the negative part is always bounded. So, so the subtleties I was worrying about defining the entropy don't apply on compact spaces. So according to what we said previously, this is a sup over phi of, what does it mean? Phi should be integrated against this measure, which is the same as composing phi with f. And integrating against mu. So this would have been defined as an integral over y, but now I'm going to define it, I'm going to express it as an integral over x. And similarly, I would have here u star composed with phi, and I'm going to integrate that against f push forward m, and that's like composing with f and integrating against m over x instead of y. And so let me call this function here psi. So the phi is maybe, let's say, an L infinity function on y, and then psi is going to be an L infinity function on x of integral psi of x d mu x minus u star of psi of x dmx. And then the only question is that maybe psi here is phi of f of x, but this is a smaller supremum. Not every function.
Robert, I think the screenshot stopped, or at least for me.
Sorry,
the screen share.
Let me share again. I hope it didn't stop too long ago.
No, like I interrupted really fast. Sorry.
Thanks. Great. So not every function on x is of the form phi composed with f, and so this is a more restricted supremum, and so that's less than SMU. Is it clear? Okay, so we have these two nice properties of the entropy, the relative entropy, namely it's weakly lower semi-continuous in both its arguments, and when you look at the image of both measures under the same mapping, the entropy goes down. There's less information in classical thermodynamics. Yeah. Okay, so I think that I'm ready to expose the main idea of the stability proof, but with a simplification. So finally, I'm going to try. Let's do the stability first of CDK infinity, and we'll worry about CDKN afterwards. But so the theorem that I'm going to prove is that I'm only going to do in compact spaces, but I'm going to say if oh yes, right. I'm not quite ready to say. I need a definition first. Great. So what's the definition? We say xk dk mk converges in measured Gromov-Hausdorff sense to x dm if and only if. So this is the definition of measured Gromov-Hausdorff convergence. MGH. So for I'm getting, so I should have said this backwards, but for a sequence of compact spaces, and a compact limit, we say that the sequence converges to the limit in measured Gromov-Hausdorff sense, if and only if. First of all, the Gromov-Hausdorff distance, well, okay. The Gromov-Hausdorff distance between the metric space here should go to 0. And one way of saying that is there exists epsilon k isometries, fk taking xk into x, with the limit as k goes to infinity of epsilon k being 0. And also, the push forward under fk of mk should converge in the weak sense to the limiting measure, i.e., the limit of as k goes to infinity of the integral of phi composed with fk dmk over xk should be phi dm for every continuous phi on the limiting space. That's what weak convergence means. Because the limiting space is compact, the continuous functions are automatically bounded. And similarly, there would be a pointed version of this for non-compact spaces. The epsilon isometries would have, there'd be a, I guess I'll give the definition. So also, well, let me save the definition for pointed spaces till next class because our time is running short, and I wanted to expose the main idea of the stability proof in this class. So, so now the theorem. This is the first stability result. Is that if xk, dk, mk in measured Gromov-Hausdorff sense converges to xdm, and xk, dk, mk is cdk infinity, both sequence and limit are compact, then the limiting space is also CDK infinity. And sometimes I may call the limiting space X infinity, D infinity, M infinity is also CDK infinity. And there should be a version of this for CDKN as well, but let me start with the CDK infinity statement, and then we'll worry about, maybe next class, we'll worry about CDKN. But to be honest, this compactness business is natural in the context of CDKN when it is finite. It's not so natural in the context, as we saw, it's not so natural in the context where at least these spaces would be locally compact and sigma compact. It's not so natural when the dimension parameter is infinity, but anyhow, to show you the idea, this is just fine. And so I'm going to do a simplification of the proof. So the proof ought to be given mu naught and mu one in probability measures on the limiting space, and they should be on the limiting space, so X infinity, D infinity, M infinity. We claim there exists a D infinity, sorry, a D2 X infinity geodesic mu t with these endpoints. With mu0, mu1 is above, such that the relative entropy of mu t with respect to mu m should be less than 1 minus t, the relative entropy of mu naught with respect to mu m, plus t, the relative entropy of mu 1 with respect to mu m, and then minus, if k is non-zero, you'd have a term minus, which is quadratic in t, and then you'd have times the limiting Wasserstein 2 distance between mu naught and mu 1 squared. So squared, and then this would be, of course, in X infinity. And so where are we going to get such a thing? Well, what we know is that the approximating spaces are in CDK infinity. We know there exist, let's say, epsilon k isometries fk, taking the approximating space is xk with epsilon k going to 0, and fk push forward, mk going weakly to the limiting guy, infinity. And we also know okay, so hang on. So we're given these two limiting measures that we want, and so we're going to choose mu naught k to be fk tilde push forward mu naught, and mu 1 k to be fk tilde push forward mu 1. So that gives us measures on the approximating spaces which are going to converge to these limiting measures. And I guess also right. I hope I'm doing this right. So I'm sitting here wondering whether these are really going to be finite entropy measures, but I hope they are. And somehow I wanted to say, well, I could look at f tilde k push forward m infinity, and certainly the entropy of this measure with respect to that is going to be finite if the entropy of the original measure was finite, which is, I'm happy to assume these guys have finite entropy. But let me time is short, so let me not worry right now about the details, since I'm just trying to communicate a main idea. And I'm also going to, in addition to just trying to communicate this main idea, I'm going to make some further hypothesis. So I'm going to assume for today that at least the d mu naught dm and d mu 1 dm are given by continuous densities on X, which is not always true. I mean, normally these would just be like, L1 densities. But I'm going to make this simplifying hypothesis. So this is for simplicity. And then we'll worry about getting this by approximation later. Let me try to do it under this assumption. And actually, in fact, I don't want to choose this. I think this was the wrong choice. But let me try to figure out what I do want to do. Right, so I have these continuous densities. Maybe I'll even call them rho naught and rho 1. Continuous bounded densities on this compact space, and probably non-zero. And now I'm going to construct, I'm going to be a little more constructive. I'm going to try to set rho naught k of X to be rho naught composed with fk of X. And rho 1 k, and oh yes, sorry, and I need to divide by some normalization to make sure it's a probability measure, which let's call it z naught k. And similarly, I'm going to let rho k1 of X be rho 1 composed with fk of X divided by some normalization zk, where Z naught K is basically the integral of and now let's see right, so this is rho naught integrated against Fk push forward Mk. And this is converging weak star to integral rho naught dm, which is 1 because I started with probability measures. And so I know that whatever the zk are, they're converging to 1 as k goes to infinity. And so for k large enough, the zk will be positive. And similarly, Z1k greater than 0 for k large enough. And so that these guys I just defined are going to be the densities of absolutely continuous probability measures on the xk's for k large enough. Great. And of course, I'll take mu0k to be defined as rho naught k dmk, and mu1k to be defined as rho 1k dmk. And then I want to look at, so because xk dk mk is a CDK infinity space, there exists mu t, a geodesic mu tk, t going from 0 to 1 in the probability measures on xk. Well, maybe I should, let me say it's the geodesic on P2 of xk, such that the relative entropy of mu tk with respect to mk satisfies the desired inequality. Great. And now basically what we'd like to do is pass to the limit as k goes to infinity. And what we know is, recall by the lemma, along a subsequence, there exists a uniform limit mu t infinity. And moreover, that limit is a geodesic in the limiting space P2x infinity. That's what our proposition and lemma showed, or corollary. And of course, right. So what does it mean to be a uniform limit? It means that the limit as k goes to infinity along subsequence, the subsequence in question of the supremum as t goes from 0 to 1 of the d2 distance between I'm a little, I think it's F. I think it's FK. So it's really FK push forward of this that has the uniform limit. The distance between FK push forward, UTK, and UT infinity is 0. Because these things should be defined on the same space. Okay, so and I know that I know because F is an epsilon K isometry, I know that this distance here is going to converge to the distance between the limiting endpoints. So the convergence of this last term will be fine. And I just need to know somehow, right, by our construction, we did this nice construction here for the endpoints, which is going to tell me that these two quantities here converge to the k equals infinity case as k goes to infinity. And then the final thing is to use the lower semi-continuity and the contractivity that we proved in the previous lemma to say that the S, so the lemma is supposed to tell us that S mu t infinity m infinity is less than the lim inf as k goes to infinity of the S mu tk mk. And then we're in good shape because this is less than the lim inf of all the stuff on this side, but that stuff actually converges. And I'm basically out of time, so I'm not going to try to rush anymore. But that's the strategy of the proof. And I'll say more about it on Thursday. So we somehow, yeah, so we got most of the way through it, but lemma implies this. So it's to be continued. Are there questions? But so maybe I'll just emphasize on the here, I was given the mu naught and u1, and I was willing to assume that they were continuous and had positive bounded densities. And then I constructed the rho k and rho k1, and I tried to construct them nicely enough that that I can show that these the entropies at those terms, this entropy and this entropy, converge to their limiting values. Now, on the other hand, CDKN, the weak CDN condition says given endpoints, there exists a midpoint such that I have an inequality like this, but it just tells me there exists a midpoint, and I have much less control on how well that midpoint approximates the MT infinity that I get from the Escoliar-Zella type, discontinuous Escoliar-Zella type theorem. And so I'm relieved that I only need lower semi-continuity along at the midpoints and not actual convergence of this to its value at the midpoint, because I have less control at the midpoint. That's some of the spirit of this proof. And similarly, it was an assumption that I had these continuous densities. Ultimately, I'm going to have to show it even when the density is discontinuous, but it's the same thing. I can construct, given discontinuous densities, I can construct continuous approximations where the convergence is nice at the endpoints. Then I have a geodesic for the continuous guys. I want to take a limit of that. I have less control at the midpoint, but I only need lower semi-continuity. I don't need continuity of the entropy along the midpoint. All right. So if there are no questions, I'm gonna pause the recording